Hello students, today the continuation of thermal expansion of matter, that we are going to learn through this session thermal expansion of coefficient of linear expansion, superficial expansions and the cubical expansion. So these are all one by one we'll see, and the graph related things also we'll explain. Yes students, thermal expansion. See, thermal expansion, we can say that suppose we have taken a rod, a solid rod of length L is heated through a temperature del T. So, the final length will be get increased, we have taken that is as L dash. Now, we can say that through the experiment, the coefficient of linear expansion will change by changing the length. So, changing length it is getting here because of thermal expansion, we are heating it so that it is getting increased. So, the length in increase which is directly proportional to the rise in the temperature. So, the new length we have taken that is L dash minus L into del T. And then you must know here increase in length is also directly proportional to original length. So, that we can say increasing length L dash minus L directly proportional to L dash, right? So, we can combine these two equations, we will get L dash minus L is directly proportional to L into del L, right? Or we can write here L dash minus L which is equal to directly proportional to L into del T. Okay, this is change in temperature, that is rise in temperature. Or here you can write the L dash which is equal to L into 1 plus alpha del T. And you can write here the coefficient of linear expansion alpha which is equal to L dash minus L whole divided by L into del T. That is equal to, we can say, del L divided by L into del T. So, this we can say that change in length, right? So, this relation will say that the coefficient of linear expansion which is equal to rise in, that is increase in length into whole divided by original length by rise in temperature. Okay. So, we can write that is increase in length whole divided by original length into that rise in temperature. Okay, so this is for the linear expansion. In that same way, we are going to see for the second 2D and the 3 dimension of expansion, right? So, next one is coefficient of superficial expansion. This in the same way we can take the example like a metal sheet. We have taken a solid rod before that length has to increase. Here the 2 dimensions, so that we have taken the metal sheet of the initial surface we have taken S. Now, we have heated through the temperature. So, the temperature has that increased del T, so that we have take the new surface area is changed as a S dash. So, here we can write S dash minus S into, that is directly proportional to del T. Okay. So, this is change in that length to the original length which is directly proportional to the rise in temperature. And also we can take that the second equation as in the way we can write that S dash minus S which is also directly proportional to S. That means what? We have said that explain for the increasing the surface area which is directly proportional to the original area, right? So, according with these 2 points, we can combine and get the equation of that is S dash minus S which is directly proportional to S into del T. Or we can write S dash minus S, which is equal to beta into S del T, right? So that we can write here S dash, which is equal to S into 1 plus beta del T, and then beta, which means we can say that S dash minus S whole divided by S into del T, which is equal to what? Del S by S into del T. That means what? Change in that length, change in length. That means, change in the surface area, which is whole divided by the original surface area into rise in temperature. That we can say that for the coefficient of superficial expansion, right? Now in the same way, we can explain for the coefficient of cubical expansion. How we can write? Tell me that. Yes, V dash minus V into del T, that is directly proportional to del T, which we can take it as the first one. The second equation we can take V dash minus V, which is directly proportional to V. By combining these two, we will get V dash minus V, which is equal to gamma into V del T. So gamma, which is equal to what we can take, that is the cubical expansion. It is the coefficient of cubical expansion, right? Next, students, so variation of gamma with the temperature. Look at the diagram, that is the graphical representation, which is for the variation of gamma with the temperature. This helps to know the coefficient of the cubical expansion of the substance varying with the temperature. How the cubical expansion is varying with the temperature in Kelvin. Observe this graphical expression, students. See, this is for the cubical expansion, that is the variation of the coefficient of cubical expansion of copper. We have taken copper here. First, see that the value which is increases with the temperature, and then it becomes constant with the temperature above 500 Kelvin, right? By that you may understand that this will happen if suppose we have taken a different material for the coefficient of the cubical expansion, right? Now the next one is the coefficient of cubical expansion of an ideal gas at a constant pressure. If you have taken a constant pressure, we'll get the formula as we know that PV, which is equal to nRT. Okay, so this is for the ideal gas equation as we already know. So you must know that is P into del V, which is equal to what? That is change in this. What we want? The cubical expansion. So volume has to change. So del V. P del V, which is equal to nR del T. Right? Or else we can write del V by V, which is equal to del T by T. Or del V by V into del T, which is equal to 1 by T. Or we can write gamma, which is equal to 1 by T. So from the expression, you may understood that the ideal gas, which is for the coefficient of volume, expansion decreases with increase in temperature. See, through this expression, we are going to learn about the relationship between alpha, beta and gamma. That means the linear expansion, superficial expansion and the cubical expansion. Now, we have taken that the cube of side L. The cube of side length L we have taken, so that the volume which is equal to L cube. And you people are seeing that already we have seen the expression for that. The linear expansion, that is we know that del L by L, which is equal to alpha del T. And you know that del A by A, which is equal to 2 alpha by 2 alpha del T. How this 2 alpha del T and 3 alpha del T came? That is only we are going to learn through this expression, students. Right. Suppose we are now heating the cube which is heated, so that what will happen? The change will happen in the temperature, right? So the change which is happening in the temperature, we can write the expression as, that means the new L which is L dash, which is equal to L plus dull L, which is equal to, we can say that L plus alpha L into dull L, which is equal to L into L plus alpha dull T, right? Now V dash, then V dash volume in change, we have taken L cube, so that we can write V dash which is equal to L dash cube, which is equal to L cube into 1 plus alpha into dull T whole cube, which is equal to V into 1 plus 3 alpha dull T plus, so we can write 3 alpha dull T. This we are the expression we have seeing that 1 plus 3 alpha into dull T plus 3 alpha square into dull T square plus alpha cube dull T cube. So this expression part which is for the V, that is the change in the volume. Now this V dash which is equal to, we can write V into 1 plus 3 alpha dull T. We can convert and write in this way. So this gamma is what? Gamma, as from the cubical expression we know that gamma which is equal to dull V by V into dull T. That is the change in the volume, original volume into this rise in temperature. From this we can write V dash minus V whole divided by V into dull T, right? Here we can write V into 1 plus 3 alpha dull T minus V whole divided by V into dull T. That is equal to 3 alpha, right? Now beta which is equal to, we can say 2 alpha also. From this we can write then the relation between the alpha, beta and the gamma, that is alpha by 1 which is equal to beta by 2 which is equal to gamma by 3, right? Yes students, so far we have learnt about the thermal expansion in detail. You might have understood. Thank you students.